In this lecture, we'll be learning about random walks, and we will see how that ties into our modeling of asset returns and gets us to a model for asset prices. So let's start with the idea of a random walk. Suppose we have a sequence, Z1, Z2, Z3, so on and so forth, of independent, identically distributed random variables, each of which has mean mu and variance sigma squared. We let S naught be an initial value, and we define our random walk, ST, as S naught plus Z1, Z2, up to ZT for natural number values for T. This creates a sequence of STs, starting at S naught, called a random walk. The Z sub I are called its steps. Mu is called the drift, and sigma is called the volatility. So if we illustrate this, suppose we're starting off at some initial value S naught. At time 1, we generate this step, so this random step, Z1. And let's suppose it's a positive step. Thus, S1 is S naught plus Z1, so it's going to be higher than S naught. So we take this step upward. Suppose then Z2 is also positive, so S2 is S naught plus Z1, so this value here, plus Z2, another positive step, and we get here. And we continue this way. Suppose that the third step is a negative step, and so our process moves down. If the fourth step is negative, we move down again. And the idea behind this is that if you are looking from above, think of this as footprints in the snow, as someone is walking in the positive T direction. You can think of it like someone who's kind of stumbling through the snow. If mu is positive, we call it a drift because this person's path should be drifting upward. The standard deviation of the steps, sigma, is called the volatility because that gives a measure of how wide these steps tend to be, which will make a higher volatility will result in a more jagged path. Let's look at how the variance and the expectation work out. So first, if we take our expected value, this is the expectation of what we have in equation 2 here. And linearity of expectation allows us to write this as the sum of the expectations, expectation of x naught plus expectation of Z1 up to expectation of ZT. First of all, S naught is a constant, so the expectation of a constant is just a constant. And each one of these Zi's, remember, has mean mu. But there are T copies of these mu's, which means our result is S naught plus mu times T. And this makes sense intuitively because if this is the value of the expected value of our random walk, and the steps have an average value of mu, then after T steps we expect to be where we started plus that average value of the steps times the number of steps we've taken. And so this is what we get for an expected value. For a variance calculation, we know we have the variance of S naught plus Z1 up to ZT. And we have to be a bit careful here. This variance will be the variance of S naught, so the variance of the individual terms, plus the sum, and goes from 1 to T, of the variance of Zn. But then we have some cross terms. And so we have S naught paired with every one of these Zn's. And you can think of it as every Zn paired with S naught. We get sum n equals 1 to T of the covariance of S naught and Zn. And then we have every possible pairing of the Z's, taking into account that we have already counted the case where Zn is paired with itself, which we've done on purpose. And so we have a double sum. N goes from 1 to t. M goes from 1 to t, restricted to the cases where n and m are not equal, the covariance of Zn and Zm. And we now note that because S naught is a constant, its variance is 0. Also, its covariance with all of the Zn's is 0 because it's a constant. That is going to be something that you can check fairly quickly from the definition of covariance. And when the n and m indices differ, the covariance between Zn and Zm is 0 because Zn and Zm are independent. We usually use the perpendicular sign for independence in probability theory. And this leaves us with only this term here. And so this is the sum n equals 1 to t. Recall that the Zn's had variance sigma squared. And so this is t copies of sigma squared. And so we have sigma squared t for the variance of our random walk. And so we have that summed up here, but with the mean of our random walk and the variance of our random walk, we can depict this. This line here would be that drift line. So we start out here at S naught, and as time goes along, we take these steps, these random steps, but the idea is this path here is what we expect on average for the process. And then using that variance, these are single standard deviation bands. So this gives us an idea pictorially of how our process should behave, but you get some kind of jagged path that looks like this. Now, bearing in mind that we want some type of random process to model an asset price like a stock price, this already looks like we're not quite there. This horizontal line here represents S equals 0. And we see it's pretty likely that this dips below 0. It can happen easily. So we don't want a model like that for something like a stock price because it shouldn't really hit 0. So we go a step further. And now let's write little r sub I for our IID random variables, our steps, with mean, mu, and variance sigma square. And let p naught be an initial value. And we define this new type of random walk here as what we call a geometric random walk. So now we have pt as p naught times e raised to the sum of those steps. Again, mu is called the drift, and sigma is called the volatility. Now, one thing we notice here is that as long as you choose p naught to be positive, pt will also be positive, because pt is this p naught, which is positive, times an exponential, which is always positive. And so this makes it already a little more appropriate for something like a stock price model. And let's note, it's not an accident that we chose little r's for our steps here, or p for the value. Think log returns and price, which we will now flesh out. But it's important to talk about the case where the steps we assume to be normal, mean, mu, variance, sigma squared. In that case, our geometric random walk, let's take the natural log of both sides. So go back to our equation here and note that if you take the natural log of pt, on the right-hand side you get natural log of p naught e to the sum of the steps. And the properties of natural log mean this is natural log of p naught plus natural log of the exponential. And because the natural log and the exponential are inverses, they undo one another, and we're left with this expression here. So the natural log of pt is the natural log of p naught, which again is a constant, plus the sum of these steps. And recall that if those steps are normal, a sum of normal random variables is also normal. So the natural log of pt in this case is a random walk, like we looked at initially. That means its expectation is, as we had done before, the starting value plus mu t, and its variance is sigma squared t. But it's important to note, we're not talking about pt itself here. We're talking about the natural log. And this is why we call pt a log normal random variable, and we use mu and sigma squared. When we write it this way, we don't mean that mu and sigma squared are the mean and variance of pt. We mean that natural log of pt is normal with mean mu and variance sigma squared. So if you take the log of pt, you get a normal random variable. Here are some properties of the log normal. Its expectation is p naught e to the mu t plus sigma squared over 2t. Its median is different than its expectation, is p naught e to the mu t, so its median is a little bit less than its mean. And its variance is given here, which is a little bit of a complicated expression. If you have seen option pricing theory before, you will recognize some of this stuff from having worked with Ito's formula and, say, the Black-Scholes model. But this you can think of as a discretized version of a geometric Brownian motion. This is the density for the log normal. And so you see it has most of its probability mass here in the middle of the distribution, but it has what we call a right skew. So the log normal density, the log normal distribution, is something that you could use to give a sense of how you may use it in reality. You may use it to model, say, the distribution of income in a country where most of the people, their income is clustered around the mean and the median in the shoulders of the distribution, but then you get some really, really wealthy people. But there are fewer and fewer of them as you go down here. If this axis horizontally represented, say, annual salary or net worth or something like this. But this is the density function for the log normal. And so this is the distribution for PT as we defined it. We can look at the expected path for our geometric random walk. So that's that curve here in the middle. And then these confidence bands are one standard deviation above and below the path we expect. And our geometric random walk will look something like this, where we start out and then we take a random step at each time. And we get this kind of path. The difference is its drift is this exponential, which you can think of kind of like a savings account on average. So remember, when you do exponential growth, you learn about continuous compounding, and that's how you get your e to the RT for your bank account if you have a savings account, right? We would usually say your savings account is e to the RT times whatever your initial deposit was. And so you can think of this in the middle as representing that, and the random walk is adding randomness to that. So this is looking like something that could work for a stock price or an asset price. And here, we now officially tie it together with all the work that we did with returns. So here we have our equation for the geometric random walk from the previous slide. Let's think back to our lecture on returns and recall how we calculated a t-period gross return. So we are now thinking of being at time t, so think of it as day t, and we want to know what is the gross return over this time period. Well, by definition, that t-period gross return at time t is the asset price at time t divided by the asset price at the beginning of the period. So that gives us our gross return over the whole holding period from time 0 to time t. But then we note we can do this telescoping trick where we throw in this pt minus 1 in the denominator and in the numerator. Same with pt minus 2, numerator and denominator, p2 and p1. And we see that we have all this cancellation that happens here. And so we would have our pt over p naught. But when we write it this way, we note that this first term, pt over pt minus 1, is the single period gross return for day t. The second term is the single period gross return for time t minus 1, all the way down to the single period gross return for first period. And recall that the way we define our log return, here we define it as little r sub I is the log of the gross return. So the single period gross return, we take its log, we get the single period log return. But now take both of these sides and put them in the power of e. And that gives us 1 plus ri is equal to e to the little ri. Now that means we can take this and substitute up here. We have e to the little rt, e to the little rt minus 1, all the way down to e to the little r1. Putting this all together, we now want to concentrate on this term and this expression. Doing that, we have pt over p naught is equal to the product of these e to the rt terms. But these all have the same base, so we can write it as e to the sum of the r's. And the key thing to notice is if you multiply both sides of this equation 9 by p naught, what do we actually get? Well, we get exactly equation 6. And we now see that this geometric random walk model syncs up with our model for an asset price based on the use of gross returns over t periods, writing it in terms of log returns, and we get exactly our geometric random walk. So think of this as syncing up what we just presented on geometric random walks and everything that we've done up to this point based on asset returns. And we now have the standard model for a risky asset price in discrete time, the geometric random walk. And we see how it ties in to our returns models.